All right, let's just jump right in. You see these massive skyscrapers scraping the clouds, and they feel like these ultimate symbols of human ambition, right? But what you don't see is that they're locked in this constant, totally invisible battle with, well, with the wind. So today, we're going to explore how these giants actually manage to stay standing. And here's a hint. It's not just about being strong, it's about being unbelievably smart.
Wow. I mean, that really gets to the core of it, doesn't it? It's not about some huge hurricane force gust of wind just knocking a building over. No, no. The real danger, it's a gentle, rhythmic pulse. Something that finds the building's secret weak spot and uses its own natural movement against it. It's this incredible phenomenon called resonance. And believe me, it is the thing that keeps structural engineers up at night.
So to really get a handle on this danger, we've got to listen to the building itself. Because yeah, every single skyscraper has a hidden rhythm, a secret pulse. Just think of a guitar string for a second. When you pluck it, it vibrates at a very specific pitch. That's its natural frequency. Well, a skyscraper is exactly the same. Every single one has its own unique rhythm that it just wants to sway at when the wind gives it a little nudge. It's not a flaw, it's just physics. And this is absolutely crucial to understand, that flexibility is a feature, not a bug. If you built a skyscraper that was perfectly rigid, it would be brittle. It could just snap. So engineers actually designed them to bend and flex to absorb all that wind energy. But that intentional sway is exactly what opens the door to the danger of resonance. So how does a simple breeze build up into a force that could potentially take down a building? Well, the wind isn't just brute force. You got to think of it more like a musician that can play a building like an instrument. And if it hits the wrong note, the results can be absolutely disastrous.
Okay, so this is the secret to the wind's rhythm. As wind flows past a big, flat object like a skyscraper, it can't just wrap around it smoothly. Instead, it peels off the sides in these little swirling vortexes, first on one side, then the other. And this creates a steady push-pull on the building. It's this constant rhythmic suction force.
Okay, so here's where it gets really dangerous. This is how it all comes together. The wind creates those vortices, which sets up a rhythm. Now, if that rhythm happens to perfectly match the building's own natural frequency, well, that's when you're in trouble. Every little push from the wind adds more energy, amplifying the sway. It's just like pushing a kid on a swing at the perfect moment. They go higher and higher. The building rocks more and more violently until it could actually fail. And this isn't just some abstract theory. This exact problem brought one of New York City's most famous skyscrapers to the very brink of total collapse, and the public had absolutely no idea. This story just perfectly illustrates the stakes. So the Citicorp Center had this incredible revolutionary design, but to save a little money, a change was made from welded joints to bolted joints, creating a huge weakness. Then, an engineering student asks a question that makes them realize that winds hitting the building's corners, these quartering winds, put 40% more stress on those weaker joints. It was a fatal flaw. For weeks, a secret team worked every single night, welding huge steel plates over the joints, racing against hurricane season to stop a catastrophe right in the middle of Manhattan. The Citicorp crisis was a massive, massive wake-up call for the entire industry. So how do you stop the wind from finding a building's rhythm? Well, you have to design the building to be a terrible instrument. You have to confuse the wind. And architects have a whole bag of tricks to do this. You can taper the building so it gets skinnier as it goes up. That means there's just less building for the wind to push against at the top where the wind is strongest. Or you can soften the corners, maybe add little cutouts like they did on Taipei 101. That just scrambles the airflow, weakens those vortices, and reduced its sway by a whopping 25%. And sometimes you literally just punch holes in the building to let the wind pass right through. These little adjustments are great, but for the mega tall towers we see today, engineers have to go way further. They make disrupting the wind the central idea of the entire design. Just look at this Shanghai tower, that gorgeous, dramatic spiral. It's not just for looks. It is a highly engineered feature that basically guides the wind up and around the building, so those vortices never get a chance to get organized. A design like this just wasn't possible before modern computers, and it was so effective it cut the wind load by almost a quarter and saved them an insane $58 million in steel. And then you've got the king of them all, right? The Burj Khalifa. It uses a totally different strategy. As it rises, it has all these asymmetrical setbacks. They call it a discrete spiral, which basically means the building's shape is constantly changing at every single level. So the wind, it literally can't find a consistent surface to grab onto. There's no way for those vortices to get organized and find a steady rhythm. The design is built to, you guessed it, confuse the wind. It's just genius.
So shaping the outside of the building is a really powerful first line of defense. But for the incredibly tall and skinny skyscrapers popping up today, engineers needed one more trick up their sleeve, a way to fight the sway from the inside.
You know, as these towers get taller and way more slender, like 432 Park Avenue in New York with its crazy 1:15 width to height ratio, aerodynamics alone just can't do the job. At those heights, even a small, safe sway can be really unsettling for the people inside. It can even make them feel sick, so you need an active system to counteract the wind's push. And that's where the tuned mass damper comes in. It's basically a giant passive counterweight. As the building sways one way, this massive weight, which is tuned to the building's exact natural frequency, sways the other way, completely out of phase. It acts like a giant shock absorber, soaking up the kinetic energy from the wind and basically canceling out the motion.
And when I say massive, I mean massive. That's the weight of the tuned mass damper inside Taipei 101. It is a giant steel pendulum, a sphere of gold-painted steel plates just hanging near the top of the tower for everyone to see, with the sole purpose of pushing back against the wind. And what's so cool is that these incredible feats of engineering, which used to be hidden away on mechanical floors, are now being celebrated. The damper in Taipei 101 is a genuine tourist attraction. They even made cute cartoon mascots for it called the Damper Babies. It's engineering as public art. Now, besides those huge solid weights, there's another, much simpler approach: slosh tanks. And they are pretty much what they sound like, just giant tanks of water. As the building sways, all that water sloshes back and forth, and the displacement of all that weight provides a similar counteracting force. It's a much more low-tech way to stabilize the building.
So here's the really crucial point. The next time you look up at a super tall skyscraper, don't just see a static structure. See a dynamic system, an instrument tuned to absolute perfection. It isn't just bracing against the wind, it's actively, intelligently, and even elegantly dancing with it, all to achieve an impossible stillness.
This constant battle against the wind has pushed engineering to incredible new places. But as we keep pushing the boundaries, reaching higher and higher into the sky, it really makes you wonder, what other hidden forces are waiting for us up there, and what new kind of genius will it take to outsmart them?